Okay, good morning everybody. I hope everyone's having a wonderful day. So just before I get started, I will be putting out assignment number 3 as soon as possible. So it'll probably be this evening. I'll probably give you a little bit extra time for the submission itself. So I just feel like that's only fair to my students. So I'm hoping you're going to look forward to this. This lecture and next lecture are going to be very related to the final assignment. So just keep that in mind. But a lot of it we've actually already talked about. It's just that there's one small tweak to the way we're setting things up because you're going to be working on hashing. We're going to kind of beef it up with another data structure. So anyways, I wanted to start off today by giving you a more specialized version of a dictionary. So remember, a dictionary contains records with key value pairs or key data pairs like this, where all the keys are unique. Suppose I know more about my keys, for example. Say, for example, the keys actually are of some data type that is comparable, for example. Very common, very common. But a lot of the things we talked about up to this point didn't make any presumptions about the keys. So everything we talked about with hashing and everything, they involved general dictionaries where we just have keys and that's all we know, right? So what we're going to do today is we're going to start talking about how we can approach ordered dictionary. So this is a kind of dictionary, or called an ordered map. So it's a specific kind. So it's a certain configuration for a dictionary, where all the keys in this dictionary have to form what we call a total ordering, or total order. Now, you might ask, Dan, what is a total order? Well, here's the great part. So all it means is I can give you any two keys, and you should be able to tell me that one key is less than the other key, one key is equal to another key, or one key is greater than another key. That's all it means. So you know just how we talked about comparable elements earlier on in the course? That's all I'm talking about. So you know all sorts of different types of keys that work for this. For example, like ints, like integers. Strings also work like this too. These are all examples of keys that can form a total order like this, or total ordering. So are there any questions so far? So it's just a dictionary where we're going to ensure that the keys always have this ability to be compared like this. That's the only thing we're adding. So once I have this, I can also define more operations. So sure, technically speaking, I'm adding some more. So we have our get, put, and remove operations. We also had some other ones like is empty and size. But I'm going to add in these other ones that we can also study. So these are some other common operations. So for example, there's here called smallest. So what this does is it returns a record with the smallest key. Makes sense, right? Largest, same idea. Returns the record with the largest key. Then you have predecessor and successor. Now, at first when you see these, you're like, oh, what does that mean? So let me be careful with stating this. So predecessor, where I give you a key, returns the record with the largest key that is less than k. So that means that if I give you something like, if I give you a bunch of records that have keys that look like this, I say 1, 2, 5, so 4, let's go 4, 5, 10. And I say, hey, look, suppose I give you k is 4. What would be the predecessor of 4? So it is the record with largest key that is less than k. It would be the record with key 2. Exactly. That's all it is. That's all it is. So note that it's less than as opposed to less than or equal. So if I gave you 4, you should give me the one that comes just before it. So very often the way you can look at predecessors, I give you you can almost imagine this like a record, where what you have is you have the 4. I want to know what precedes it, hence its name, a predecessor. What comes just before it. That's very often how it gets used. Likewise, there's a successor. So this is returning the record with smallest key that's greater than k. So likewise, if I gave you k is 4, what's the successor of 4? So what's the successor of 4? It's 5. It's the one that comes after. Yeah, it's just, that's all it means. That's what successor means, right? what comes after this key? So what if there are two 4s that are less than? Now, remember, this is a dictionary, right? This is a dictionary, so all the keys are unique. So there cannot be two 4s. That's a good question. So just remember, it's still a dictionary, so it has unique keys. So it means that there can't be two records with the same key. That's a really good point to bring up. Just to remind ourselves, remember that the dictionary contains key value pairs. So it means that all the keys are unique. So if I were, for example, to show you that two records had the same key, you know it's a duplicate, you're not allowed to have those. So in fact, you're going to very often see when we actually look at order dictionaries, you're either going to have it where they're all going to be from smallest to largest. There's going to be none that are going to be equal to each other. Sure. So a question about hash tables. Are they made of dictionaries? So just to clarify, we have the idea of a dictionary, which has, for example, the get, put, and remove operations. So this is an abstract data type. So just like when we talk about a stack or a queue, those are abstract data types as well, where they have defined operations. And each one of those operations is a description of what we would like to perform. When we come to the actual data structure, I would like to implement the abstract data type. Then that is the question of what we do with that. So for example, you can have a dictionary that is implemented using a hash table. So the relationship is that I give you an abstract data type, I would like to implement it. So I describe the how, like we talked about earlier on in the course. So I have a dictionary. You can imagine it like a problem statement where I give you a bunch of records and I want to know how I can get them, I can put them, and I can remove them. And I want to do it as fast as I can, all three of them. So now I've just allowed it to have this additional property. So just with a hash table, so you can implement a hash table. Yeah. So for example, you'll see that in some implementations of dictionaries, they use an underlying hash table. Sometimes they actually use just a discrete data structure like we're going to see. We're going to see, for example, something called a binary search tree here today. Where what you do is it actually implements all the operations. But you can augment, for example, something like a hash table to perform all these operations as we've seen a few lectures ago. So you can have get, put, remove, just like you would expect. Yeah, that's why you're noticing we're focusing in on get, put, and remove, because the main focus of the remainder of this course is the dictionary problem. Trying to implement these three operations or any other ones that might be relevant for us when we're studying them. So you can get an idea of how we can actually implement these things. Hopefully that clarifies that. Hopefully that's clear. So question. Could there be a situation where we run into where we have two different records because their keys are... Yeah, so remember, it can be the case that the data has the same value as other records. What matters here is the keys. So it's you think of it as a problem statement. So all the keys are distinct in a dictionary, but I must stress that most of the data structures I talk about here are easy to augment to allow for duplicate keys. Just the thing is, actually, I'll talk a little bit about this actually today. So if you're thinking, oh, damn, well, that seems rather restrictive. Actually, it's not, surprisingly. It's just that it makes our algorithms easier to describe. But yeah, it's just because this is the problem statement of sort. We want to actually implement one of these dictionaries. So we've seen a bunch of different ways to do that up to this point. We're going to see even more. So anyways, we have these operations that I'm also going to add in. So this is what an ordered dictionary is. Is the definition clear, everybody? So it's just a dictionary as we defined it before, except now the keys form this, what we call a total ordering or total order. So just you can think of the keys as like numbers or strings, and the idea is that now I can compare them. Okay, so let's proceed. So I thought we would start off a little bit of a warm-up with this, because remember, actually, we talked a little bit about this actually before. So I thought it'd be a good idea we revisit this, because I talked about it the other day, and I told you, oh, well, if we know that we can actually sort the data, or in this case, specifically the keys, we could do more. So I want to revisit this because we could actually describe this in a somewhat different way. So a very simple way of implementing an ordered dictionary is using what we sometimes call a search table. So this is just simply an ordered sequence, which of course you can store the records in a sorted array, for example, like we talked about before. So we sort them by key, all the records in this array. Or if, say, for example, using a vector or anything like that, you can index directly into it instantaneously. So what I want to do is I want to walk through each one of the operations again and see if we can remember what we can do with this search table, this idea here where I have a sorted array, and I want to implement the ordered dictionary. So remember, I have the get, put, and remove operations, so we're going to talk about these. So remember, if I don't know anything about the keys, I can't sort the dictionary by key at all, right? But if I have this and it's in a sorted array, the get operation, how efficiently can I perform that in terms of big O? So what can I do here for the get operation? Now, the first thing you might try doing is just, okay, I'm just going to scan through my array and find the appropriate record. But you can do even better than that. Yeah, you can use binary search. Exactly. We can get a logarithmic running time here, right? Because it's a sorted array. The keys are sorted from smallest to largest. So all I'm doing is I'm accessing the keys when I do these comparisons, when I make my guess, when I find the middle spot, right? So I could do this in big O of log n time using binary search on the keys. Okay, that H is looking a little sad. Let's fix that. On the keys. So we know we can do this rather nicely. Whoops, I forgot an N right there. There we go. My apologies. So we got the get operation, put and remove. We actually talked a little bit about this the previous lecture. Now, I could, of course, find where I need to perform the insertion. I can do something like that, but remember, it's a sorted array too, so I have to maintain the ordering in my sorted array, right? Well, let's think about it. Suppose I gave you an array that's pretty much full, and say, for example, I need to put this somewhere near the beginning. Like, say it's right at the beginning. What do I have to do with all those other records? Can they just like stay in the same spots, or do I have to like move them all over by one? Yeah, I'm gonna have to shuffle them all over by one, right? So I gotta do this a little bit more carefully than just simply I can just have magically the ability to like create more space in between. That just doesn't happen with an array. So in this case, we can of course do this in linear time. And of course, remove. How about remove? Can we do this any faster, or is it still linear time? Yeah, we're going to have to deal with linear time again because remember, it's a sorted array. And say, for example, I could use binary search to find the spot of the thing I'm looking for, right? It'll tell me in logarithmic time if it's there or not. However, like we just talked about here, suppose, for example, I need to remove the very first record in the array. And I want to use binary search. Well, I can't just simply remove the first spot and just leave a blank right there. Suppose that this happens several times even. You would leave a whole bunch of gaps in your array. And that's not something that binary search is going to very much like. If binary search could like something, I don't know, like ice cream or something. These gaps will cause problems for binary search because it won't know what a blank is. You would have to put some marker in there or something. But the point is it's going to mess around with some of these other operations, right? So what we do is we can just shuffle over the appropriate spots, just like this case as well for put, right? So indeed. So you notice that we can get. So in both of these cases, we have to deal with shuffling. Or potentially in the put case, you may have to actually resize the entire array, right? That's even worse. So specifically in this case, you could also, another way you could justify this to somebody is you also have to resize the whole array if the whole array becomes full, right? So notice that in this case, this is actually should match up what I told you the other day when I alluded to the fact that if I could sort the array, I can get these worst case running times. Is that clear, everybody? So I want you to think about these other operations and think about how you could perform those on a sorted array. So many of them can be achievable by, for example, I'll give you an idea. You know that, so where in a sorted array would the smallest key be? Where would it be? Yeah, like, so if I have a sorted array, remember the array will have, suppose I have some index for where the last index is versus the beginning and all that stuff. Where would it be? Would the smallest key be over here? Would it be over here? Do I know where it is? Yeah, it's at position 0. Exactly. It's at position 0. So the smallest will be right here. So you can efficiently do smallest, right? How long would that take? How long does it take to compute the smallest? It takes constant time, right? I could compute this in constant time. Do you see what I mean? Like, so many of the things you know what to do with an array are applicable in cases just like this. So like you could do the same thing with largest, right? I could just figure out where the last filled spot is, akin to the strategy we actually used when we had an array-based stack, for example. You know, I had like a position where I knew where I performed the insertion. We did something like this before with our stack, but you can also do the same thing when we insert elements into an array, right? You can do the exact same thing to compute the largest in constant time. Isn't that wonderful? But notice that in this case, you have to look at this kind of carefully. But I'll let you think about that. The point here is that we have ways to do this. That's the point. But now I would like to revisit these complexities. And notice that I have log n, I got n and n. So by the end of this course, I'll be showing you how you can achieve logarithmic times for all three of these operations. So we're not going to get there quite yet, but I'm going to need some machinery in form of another data structure to get there, okay? So let's start talking about what we're going to call binary search trees. So before that, I have to actually tell you what a binary tree is. So let's do this. So we're going to talk a little bit about binary trees first, before I define what a binary search tree is. So that when we get to the binary search tree, everything should be clear as day, and also you'll know some things more about binary trees, and specifically what we call proper binary trees. So we're going to talk about binary trees. And binary search trees. So that's going to be the main topic for today. Which I'll abbreviate binary search trees as BST very often. So we're going to talk about these a lot today. So the first thing you need to know is what a binary tree is. So it's just some jargon first before we get into anything. So remember, we talked about what a rooted tree is, right? And I mentioned about the idea of what an ordered tree is. This is where we impose an ordering on the children or nodes in the entire tree. So this is an ordered tree. An ordered tree where the number of children every node has. So the number of children every node has. Can you take a guess of how many children each node has at most? Just look at the name. So you know how I've sort of just been playing around with this? What would, when you see the word ba, and you see the prefix ba, yeah, two. Yeah, two. Yeah. So let's see. The number of children every node has is at most 2. And the thing that makes the tree ordered is the following thing. A child is labeled, actually I'll say it's either labeled, it's one or the other, is either labeled, if it exists of course, is either labeled the left child, or the right child. Presume they exist. Or the right child. So we're going to have this idea of a left and a right child. And it's always presumed that the left child comes before the right child. So left. Oh, those dogs are barking. Get over here, puppies. Come here. It's like Uncle Dan's pet store. Does anybody want to see a puppy dog? But let me get left comes before right. Before we stop our thoughts here, if she comes closer to me, I will definitely bring her up and show you. Her name's Lola. That's a little dog's bark. Comes before right. So that's what makes it an ordered tree, is the fact that we label the children left and right, and left comes before right. So I'm going to show you an example of such a thing. So here's an example of a binary tree. So, for example, I'm going to have a node here with 3 in it. That's going to be the root. You can have 2 and 8 as its children. I would call 2 the left child. So this is the left child of 3. This is the right child of 3, of node 3. So notice the way I'm actually going to draw them actually visually represents left and right now. So it isn't just a coincidence, it's actually how it's going to be drawn. So left, then right. If they exist, of course. So notice here that I'm going to have only a right child for 2. So I'm going to have 9 as the right child of 2. 8 is going to have a right child with data 4. And then I'm going to have 2 children for 4, 7, and 1. So this is what we would call a rooted binary tree. A rooted binary tree. So you might ask, okay, so Dan, what do we get as a perk from this? What we're going to see is that we can actually impose more specialized structure on a binary tree. Likewise, we can also, we know a lot about binary trees. This is because of the very simple structure they have. Their structure isn't all over the place, just like the trees we seen last lecture, where the number of children could just be there could be quite a few children in one node, then you can have another node that has very few. Here, we know it's at most 2. So one thing also you need to know is that we're going to be talking a lot about what we call proper binary trees. So when we're studying what binary search trees, we're going to be talking about proper binary trees. So every binary search tree, as we're going to define it, is what we call a proper binary tree. So this is where it's just going to be simply a binary tree. A binary tree where every internal node, remember those are not the leaf ones, these ones have at least one child, where every internal node has 2 children. And to be very specific, it has exactly 2 children. So it's not at most, it's exactly 2 children. So for example, if I look at this tree, is this a proper binary tree? Yes or no? So you could just look at each one of the internal nodes, right? And you can ask yes or no, and the answer, of course, good, very good. The answer is no. So, for example here, I'll give you another example of a binary tree, but it'll be a proper one. Here's another one. So here's just another doodle of a binary tree. So the root's going to be D. I'm going to have A and F as its children, and I'm going to have E and J as its left and right children of F. So this is the root right here. Question, is this a proper binary tree? So look at the internal nodes and ask the question, are there exactly 2 children? And the answer is yes this time. Exactly. Very good. So now what we're going to do is we're going to talk about some properties that proper binary trees actually have. And these are going to be properties that when we start talking about binary search trees, all of them are going to have these properties. So I'm going to define a binary search tree in terms of a proper binary tree, just to be clear. So I want to talk about some properties that proper binary trees actually have. And they have a lot of lovely properties, just to be very clear. You're going to find the way I define the binary search tree to be much more elegant because of the way I define our trees. But there's a lot of things we can say about proper binary trees. In fact, we can say a lot of things about binary trees on their own too. But you can really just go wild with this stuff. So let's talk about this. So I want to give you some properties. So now I'm not going to prove these for you just for the sake of time, but I'm going to try to give you some intuition around it. Yep, so the external nodes are what we call leaf nodes. So internal nodes, those are ones with at least 1 child. The external nodes are what we're calling leaf nodes. So they have no children. Yeah, so just like we had before, like for example, A, E, and J, these are all leaf nodes in this way I just drew this tree. You're going to see that the binary search tree is going to be a bit more specialized than just that. We'll see that in a moment, but let's talk about some properties that I feel like I'm just repeating myself. Some properties. So let's talk about some properties of proper binary trees. So these are all really handy. Every once in a blue moon, you find them useful to use. So these are just some properties that we have. So the first thing I'm going to tell you, now I'm going to state this one without proof. One property is that the number of leaves in a proper binary tree is equal to the number of internal nodes it has plus 1. So I'll let you think about why that might be the case, but I'm not going to talk too much about that here. I know, usually I say something, but I'm just going to keep it kind of blank here for now. So the number of leaves is going to be no more than something. It's going to be, actually, let me draw you a little bit of a doodle off to the side here. You're going to find this rather helpful for when I describe these properties to you. So what I'm going to do is I'm going to imagine I try to fill up the proper binary tree so it has as many leaf nodes as possible. So what I do is I'm just going to try to complete the binary tree by having as many children as I can at a given level of the tree. So when I say the level of a tree, I'm referring to the level of a node. So all the nodes at a given level dictate the the level of a tree. So for example, these are all the nodes with level 0. These are all the nodes that are level 1. If I can have all the nodes at level 2, and so on. So for example, this would be, so if I have the level here and the number of nodes I have, if I want to try count up how many nodes there can be at most in a proper binary tree, I can maximize this by just simply taking and having as many children as possible for every one of my internal nodes, correct? So like I could keep going through this over and over again, right? But yeah, that's exactly it. So somebody's noticed this, is that notice if I wanted a nice bound on the number of leaves, well, look at it. If I start level 0, it's 1, right? When I go to level 1, notice I have at most, I can have no more than two nodes. When I'm at level 2, I can have no more than 4, right? Well, look at this. It's going up by powers of 2, right? So that's 2 squared. And then so this is level 0, level 1, level 2, and you can keep going, right? Well, imagine that the leaf nodes are just sitting down here at some arbitrary level. Well, how deep can that be? Well, so we notice that each one of these tells us it's based on the level, right? Notice that level matches up with the exponent, right? But we have a name for this. When we have it where we try to find the highest level in the tree, what do we call that? What was that? It's the height, exactly. It's the height. So what you can say about the leaves is it can never be more than 2 to the power of the height of the tree. Likewise, just like we had just established here, or at least we discussed it here, if I look at the number of nodes at level I, this can be no more than 2 to the power of I, right? Just like we just discussed here. So if I look at any one level, the number of nodes cannot exceed that. Sometimes when we come up with some proofs later on in the course, we might use this fact. One I'm not going to prove for you here, but there's going to be something that's going to be helpful for us later on when we study a topic called AVL trees later in the course. It's going to use this property I'm going to describe here in a moment. So I'm just going to write it right here. Is that log base 2 of the number of leaves is no more than the height. So it's less than or equal to the height, but this is actually less than or equal to the number of internal nodes. So what this is, so there's 2 parts to this, right? So log base 2 of the number of leaves is no more than the height, but also you can use the number of internal nodes always as an upper bound on the height of the tree. We'll actually use this right half of this inequality later on in the course, so probably sometime next week we'll probably use it. So these are some properties I wanted you to be aware of. They're all really, sometimes you will run into a circumstance where one of these becomes very useful to think about. Usually in this course, we'll focus primarily on these 3 right here. But sometimes you'll find this one also be helpful. But I just want to bring up these few common properties that proper binary trees have. Are there any questions about these properties here? Okay, give me 2 thumbs up if we're okay here. I think we have all the machinery to define a binary search tree now. All that mustard and mayonnaise and I don't know what else that we're going to need to talk about the binary search tree. And you're going to see that everything we just talked about here is going to stack up to this definition. And I must stress that there's several ways to define a binary search tree. This is one of the more classic ones that fits perfectly into a dictionary definition. Both literally and also in the sake of talking about our ordered dictionary. So in that sense, it's sort of figurative and literally the case. Let me just... Okay, so let's get on this. So we're going to define this as the following, because then we can know all these properties, and very often it'll help us prove claims a little easier. So I'm going to define a binary search tree. So you can think of this as a formal definition. So I'll always call it a BST after this point. So it's a proper binary tree. A proper binary tree. And what's going to happen with our BST is it's going to store records in the internal nodes. It's storing It's storing records in its internal nodes. Internal nodes. Such that each internal node Each internal node U satisfies what we're going to call the binary search tree property, which is the following. So this is going to be the property that has to hold at every one of the internal nodes of our tree. So every key in the left subtree, which, to be clear, when I use the term left subtree, I'm talking about the left child subtree. So if I give you a node U, if I examine my left child and I look at its subtree, that is what we call the left subtree, just to be clear. Likewise, you can say the same thing about the right subtree. Every key in the left subtree of U is smaller than the key of U. So whatever the key of U is, you know that the left subtree, every one of the records that's stored in the left subtree will always have its value for its key less than our key. Same idea with the right subtree, except it's going to be greater. Every key in the right subtree of U is larger than key of our given key. So I'm going to draw you a picture just to summarize this, because I think you might find this a little bit more helpful than just this. So here we go. So imagine I give you node U. So this is node U, and this has to be true for every one of the internal nodes. Suppose it has key K. So it has a key K. And I look at my two children. Because it's an internal node, I can guarantee you, because it's a proper binary tree, that it has exactly two children. And here's the catch. If I were to examine at each one of the internal nodes, suppose that it did have a key. Say K1 and K2, and I examine their subtrees at these nodes. What should happen is that all of the keys in the left subtree, all of these have to be less than K. All of the ones in the right subtree have to be greater than K. So this is what we're going to call the binary search tree property. So a binary search tree has to satisfy this property, and it is also a proper binary tree. So I thought it'd be a good idea to actually draw a picture of one of these binary search trees for you so you can get an idea of what this is about. So first, are we okay with this definition? Is there anything about the definition that looks a little strange to you or anything like that? There is one thing I did not address quite yet, but I will show you in the picture next what happens with those. Does anybody see anything I haven't really talked about? Like I've said things about internal nodes, right? What about the leaves, right? Like I didn't say anything about the leaves. So let's talk about that. So you're going to see with my example here, it's going to go a little bit, you're going to see at first it's going to be a little bit strange at first. But I can assure you there's at least a couple different ways you can represent a binary search tree. But we're going to stick to one of them. You're going to get exposed to the other one during lab, because there's a couple different ways you can implement a binary search tree. So we're going to stick to the one that's close to this definition here in class and on the assignment, but in the lab you'll get exposure to this other representation I'm going to show you. So let's talk about binary search tree implementations. So the first thing you need to know is that we can adapt the linked tree implementation we had the other day. So, question. Is k value of integers or natural numbers? It doesn't make any difference as long as it's some key that maintains a total ordering. It could be strings, could be integers, could be natural numbers. Doesn't make any difference. Like I said, the keys can be many, many different types. That's a good question, though. So, anyways, there are two common ways to implement a binary search tree. So I'm going to start off with the one that I'm going to focus in on, and then I'll show you the one that in the lab you'll get exposure to. So the first one, which I'll call implementation number, okay, to be consistent with my notes, I called it 2, but I guess I'll call it 2. So the first way you could represent this, so this is an example of a binary search tree to the T of that definition over there, okay? So suppose remember I drew you a proper binary tree earlier? I'm going to show you it as a binary search tree. So I'm going to have D, which is going to be the root. So you would have, for example, an instance variable for the root. And that will point at a node. And just before I get too ahead of myself, do you remember how in our linked tree representation, we had it where we had several different attributes, right? We had data, we had the parent, and we had the children, right? But here's the thing. Do I need a large collection or something to keep track of the children here? Or can I do something a little bit more optimized here? Do I need like a big list or anything like that? Not really, no, right? I don't need a collection to store the children, right? I just need like 2 variables, one for the left, one for the right. If I don't have a left child, then simply it's null, right? If I don't have a right child, it's null, right? But the thing is, we have to keep in mind the way we represent it. So you can specialize the linked tree representation that I gave you last class, and I actually have a picture of this tree using this representation in the notes. So I will ask you to take a look at it. I'm just going to talk about the structure of the node, but otherwise it's the same idea. So you can have your data. So you have a data attribute. So this would be what a binary search tree node will look like. Is you'll have data, you'll have a pointer to the parent. Some representations of binary search trees, like I told you previously, may not necessarily have the parent, but ours will. Then you'll have a left and a right. So these will just be pointers to the left child and right child if they exist. Then the data is your data attribute, as we had last time, and the parent is a pointer to the parent node. Is that clear, everybody? So it's just a specialized version of it. And I don't need any fancy-pantsy data structures beyond that for this. So, for example, if I were to, say, draw this out, so if I had D, A, and F are the left child and right child, and I'm also going to have E and J as the left and right child of F, you'll notice that I didn't say anything about the leaf nodes up to this point. In this representation, the leaf nodes actually are placeholders or dummy nodes. So what they're doing, they're not going to contain any data. They're not going to store records. So they are a node. They are a node just like this. But they store no record. So their data attribute will be null. So it stores no records. So it stores no records. So when you're looking at this, what it would look like is would be null, 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 and you'd have a pointer to your parent. That's what these would look like. You'll see it in the example picture I have in the notes of what this would look like if you actually adapted those. That as the node right there. So this is actually how we're going to represent the binary search tree for our last assignment and here in class. So our algorithms tend to be easier to describe using this representation, but there's some benefits it has, but there's also drawbacks. So the pro of it is it makes it easier for us to design the algorithms. The drawback is it uses extra space, as you're going to see. Another way you can represent the binary search tree, so if I give you the same data, for example, right here, Notice that these are just placeholder nodes, right? They're just nodes that don't have any data in them. Somebody will stare at you for a second and be like, why would you have a node that has no data in it? Like, no, where's the data attribute? Like, why don't you, that seems like a waste of space. So here's another way you can represent the same exact binary search tree. So again, you can have the root, you can have A, F, and then you have E and J. And wherever you see one of these placeholder nodes, which are our leaf nodes over here, you're going to use null for its left child, null for its right child, null for its left child, null for its right child, null for its left, null for its right. So wherever you see one of these leaf nodes, they'll just simply be null pointer. So this is another way of representing the binary search tree. In some avenues, you'll very often run into the rightmost one because it's an optimized version of this one. So just be clear, both of these are technically representations of the same thing I have over here. Just this one, that over there is an optimized version of this. So we'll focus on this representation, but you'll get exposure to that one over there on the lab. So are there any questions? Is that clear, everybody? So the pros of that representation is that you're not wasting space anymore, but the drawback is now you have to deal with null pointers. Because you're going to find that when we work with our algorithms here, when I have these leaf nodes like this, the issue at hand is that, okay, so if I have these leaf nodes, it makes it easier for what we call anchoring for some of the algorithms we're going to see a little bit later that do operations on the tree. Over there, you'll have to check for null pointers, and you have to delicately deal with this. It doesn't change the concepts of the algorithms, it just changes out how you would implement it in terms of C++ or some other programming language. So is that clear, everybody? So we're going to stick to this representation for the assignment and in lecture. The reason why is it's purest to that definition I have over there. This is just an abbreviated version of this one on the left. But keep in mind, you can also define a binary search tree using this if you literally just use a binary tree. So whenever I ask you things about binary search trees, we're sticking to this representation, okay? Just for the sake of convention. So I have some more details about this if you're curious more about these things, including actually how this actually gets represented using one of those nodes over there. So I wanted to make two remarks for you, two remarks that are very quick, so that we can get to talking a bit more about what we can do with these binary search trees. So two remarks, because actually earlier today, I thought it would be important that I bring this up. I do have more details about it in the notes, but I want to make a couple of remarks. So it involves duplicates, because binary search trees are not distinctly used only for dictionaries. You can use them for all sorts of different things. Just the way I'm setting this up is very natural for a dictionary. So naturally, I want to address the lovely question we got earlier about duplicates. Like the issue like, oh, suppose I want to have multiple records with key 4. Well, here's the good news for you. The good news for you is that there are ways to easily change this up so that allows that to happen without changing our algorithms really a whole lot, which is great. So it depends on if the keys matter or not. So if the keys matter, but not the data, so if the data doesn't matter, what you could do is you could augment your nodes. You augment this node with a counter. So you know how we had like a counter that keeps track of the number of elements we had? What you do is you keep track of so you have a counter. You have a counter at each one of the nodes. If you get a duplicate key come in, if you aren't implementing a dictionary and you want to have duplicate keys, you just have a counter. So you would just increment this counter every single time you get an insertion with that given record. And the only thing that will change in our algorithms is if you do a removal, you'll decrement this counter down until you hit, if you're at 1, then you know you actually have to get rid of the node. So that's how you can deal with duplicates if the data doesn't matter. But if it does matter, if both matter, give each node a collection or container, whichever is appropriate for your application. For example, a list. For data. So instead of just having it where just the data is just a singular object that you're pointing at, instead what you would have is you'd actually have a collection of those records. So actually, they wouldn't technically call them records, but they would be your elements you're placing in. So you would just keep track of all of the data objects that you're pointing at in this collection. Is that clear, everybody? So you can easily modify everything we're talking about here to permit these to happen. So remember, the point here is it doesn't have to be the case that the keys have to be distinct. But the thing is, for our algorithms, it's very natural to write it that way. In fact, some of our algorithms actually are permitted to allow for duplicate keys to occur in the algorithm itself, which with some modifications, of course. So if that's the case, are we doing okay here so far? Hopefully I addressed your lovely question earlier from about what you do with the duplicates. So if you ever find yourself dealing with duplicates, which you won't have to worry about for the assignment, but most certainly if you ever try using one of these trees, these are two common ways you can deal with this while having these exact same algorithms that we're using here. But they don't really, these are nice things you can do. But yeah, so anyways, let's start talking about what we could do with the binary search tree that specializes things. So first I want to revisit tree traversals. That's something we'll talk more about in something like CS340. They're related to trees. We're going to talk about tree traversals again, but in the context of binary search trees. So one thing I want to stress is that all of these tree traversals, I've also provided pseudocode in the notes that also show you what each one of them would look like if you try to use this binary search tree. So we're going to talk about what we call an in-order traversal. So this is an additional traversal approach you can use specifically when you have the binary search tree property in place or something akin to it. As you're going to see, we can generalize this idea later on in the course. So in a binary search tree, it visits all the nodes, specifically the keys. Usually when we talk about this, we don't really care a whole lot about the leaf nodes, but sometimes it's helpful to have that information for certain applications. But we're going to focus on the keys. The keys in increasing order. So, suppose I give you this binary search tree. So the root's going to be 10. So you're going to find very often, just by the way I draw it, you should be able to tell very quickly what the root should be. So in this case, the root is 10. Notice I always draw it at the top like this. It's very easy to know what the root should be. But remember, if ever it's unclear, just clarify what the root is. So in our context, we're always talking about rooted trees, but in some other context, it might be not necessarily rooted. And this actually might just be a general structure that looks like a tree, but it doesn't necessarily have a designated root like this. So we have our leaves. I'm just going to throw in here. So here are our nodes here. So I have 10, 7, 13, 2, 11, 16, and 3 right here. So what I'm going to do is I'm going to perform what we call an in-order traversal. So this is the order in which you visit things. So you know how we had, where what we do is we visit all of our children first, then we visit ourselves. What kind of ordering was that again? If I visit all the children first before myself? That was post-order, exactly. Pre-order is when you have it the other way around, exactly. So when it's in order, as the name suggests, we actually have additional information we can use here. So here we go. What you can do, so first you can, if of course it exists. So if key exists, so for example, if you're looking for the keys, then you call you call the in-order traversal on the left child. That's the first thing you do. And then the second thing is you visit yourself. And then, of course, you do if there's a key that exists. You could just call in order on the right child. So just to clarify, the whole order we're doing things in is left, myself, then right. That's the order we're going in. And you're going to see with a binary search tree, it guarantees we're going to visit all of the keys in sorted order. So watch this carefully. So, in fact, when you look at the pseudocode, you'll see it's very similar to the other traversals we talked about. In fact, it's a little, I would argue it has a few conditions depending on if you want to visit the leaves or not. So if you don't want to go to these leaves, there's if statements there just for that. But if you actually want to visit the leaves, just make sure you don't go too far down. You don't want to go down to null. You're going to run into some problems with that one. So if I'm doing an inner traversal, okay, so first I start up here. Suppose I do the inner traversal starting right here. I go left. I'm at a node. I go left. Oh, wait, I can't go left because there's no key there, right? So I get 2. Then I visited myself, right? Then I go right. I go left. I visit myself. I don't have to go right because that's a leaf. Then I'm done this one. I'm done here. I visit myself. I have a leaf node here, so I don't need to do anything. I visit myself. Then I go right. But I don't visit that one quite yet, right? I go left first. So I go left. This is a leaf, so I don't do that. 11. Go right. Nothing there. Okay, now I visit myself. Then I go right. Then I go left. Nothing there. Myself. Go right. And I'm done. Notice that all of the keys are in sorted order. Does anybody see anything interesting that comes as a result of this? I suppose I gave you one of these trees. What can I say about the keys? What could you do to give me a sorted version of all of the records? What could you do? So we've talked about sorting before, right? What if I use the binary search tree to store all of my records? So what can I do if ever I want to perform a sort operation? Does anybody see what we could do? So what would be a sorting algorithm if I gave you a binary search tree? Like say if I gave you the root of the binary search tree and I said, hey, look, tell me how I would sort all of the data in this collection. What could I do to achieve this? Well, isn't this neat? So I've actually given you the entire recipe, right? So what you would do in that case is, say, for example, you want to collect up a bunch of objects. What you could do is you could put them, like, for example, in a vector or a list or some other container. And what you do is you just carry this along like a little bag. And you can say, hey, look, I'm going to do the in-order traversal on the tree. And I'm going to follow the ordering of the in-order traversal. Each time I visit, I'm going to insert it into this container. So I just put it in there. I collect them up like I'm collecting them into a bag. But the thing is, I maintain the ordering that I visit them in. So in this case, if you use, for example, a vector, for example, as you're going to see on the assignment, what you could do is you could actually just put it at the back of the vector, or if you insert at the end of your list. If you do something like this, you can guarantee you get all of the records in sorted order like this. You could just return me back what that collection is, or a pointer to it. Is that slick? So we actually, by having this structure forces that ordering on us. So I've given you another way to do that. Now I have a question for you. based on the discussions we had last day, remember we seen like different tree traversals, right? We looked at, for example, when we computed the height, what was the worst case time complexity when we computed the height? What did we do? Well, we visit each one of the children, but the thing is we visit all of them then ourselves, right? But the thing is it takes linear time, right? Well, notice that this process also takes linear time. If you actually go through the same kind of analysis, you'll notice that it's just still we visit all the children, but we just do it in a different order, right? It's just that we visit the left one, then we go to the left, we visit ourselves, then we go to the right. We're still visiting all of our children and ourselves, but the work we do at ourselves, presuming it takes constant time to do it, what we can do is we actually can guarantee we can do sorting with a binary search tree in linear time like this. Is that fascinating? So as long as we can build one of these structures, we can actually sort using it. So just keep that in the back of your mind. Like take it, imagine it's like a feather, put it in the back like this, be like, I'm gonna keep that for later. So just keep in mind, there's sort of a catch to this though, we haven't gotten to quite yet. But the point is that in-order traversals allow us to design sorting algorithms for trees. So remember that if the tree isn't a binary search tree, you can't guarantee this property. You can't guarantee that if you did an in-order traversal, it gives you the keys sorted like this. So, one other remark I wanted to make is that you can, of course, do pre-order, post-order, like we did last time on these. So just as an example, I thought I would walk you through how we could do each of these. So this would be in order, right? Let's do pre-order first, and then we'll do post-order. So remember, the whole idea with pre-order is you visit yourself first, and then you visit your children. In this case, since it's an order tree, you visit your left, then your right, assuming that there is a key that's there. So here we go. So I'm going to visit 10 first. So I visit 10, then I go left, right, and then I visit myself. So 7. And then I go left. Okay, then I got 2. Then, okay, I can't go left anymore. I'm going to go right. So I get 3. Then I'm done there. I go back up. Okay, so now I have, let's see, I need to go right now, right? Because that's the next child over. So I got 13. So I got 3, 13. And then I go left first, 11. And then I go 16 left. So remember, I visit myself first before my children. In post order, we do the opposite. We visit our children first, and then we visit ourselves. So let's do this. Okay. So I start up here. I don't visit myself yet, right? I have to visit my children first. So I go left first because it's an ordered tree. I go left first. I don't have to go through my children first, right? Same thing here. So notice that I visit 3 first because I have to visit all my children first, right? So I visit my children. I'm done here. Okay, so now I've examined all my children here. Okay, I'm going to visit 2. Now I'm done examining this right here, so I'm done here. I have no other children here, so I could just get 7. And then I can go examine my next child over, right? Because I have to examine my children before myself, right? So I got my next child over here. I'm going to now examine 11. And now I go to now I have nothing else here, so I'm going to go to my next child for 13, which is 16. And then, of course, you have 13 because I've examined my children. And, of course, now I've examined all my children from the root, and I get 10. So one thing I do want to make a remark about, I didn't have a chance to really mention this to you, except I kind of casually mentioned it, is that, like I mentioned to you before, post-order, since I visit all my children first, very often this is useful if you ever have to do kind of like surgery on your tree. For example, one place you'll encounter this is if you actually want to delete the tree, or delete even a specific node in the tree, or the subtree at a given node. So for example, if you do a post-order traversal, and say for example you encounter, if you do this in this order, for example, if I wanted to delete every one of the nodes in the tree, I can safely ensure that if I follow the post-order traversal, that I don't delete something I'm already going to need. So for example, notice that if I go 3 here, if I delete this one, none of the other nodes affect this, right? Because that's just one subtree, but it's the smallest one at that time that has not yet been deleted. Then if I delete this, notice that 2 doesn't depend on 3, other than it used to be its right child, right? So you can actually use the post-order traversal, for example, for actually deleting the tree, because it safely ensures that you're not going to affect other parts of the tree. So you can do this with all sorts of fun things with that. So I felt like I just wanted to mention that. But there's one other kind of traversal that I'm not going to talk about here so much in detail, but believe it or not, you can actually adapt a queue to traverse the tree as well. It's using something called a level order traversal. So I want you to just read about this in the notes. It's on page 111. I'm going to walk you through the idea here. And actually, I give an explanation of how you do this. It actually uses a queue. So the idea is that you start off with the queue entering in the root. So you enqueue in the root. And then what you do is you dequeue off whatever's at the front of your queue, which in this case it's the root. I examine if it has a left and a right child. If it has a left, I put that into the queue. If I have a right, I put that into the queue. But whenever I encounter whatever is at the front, it's going to correspond to me exploring the tree as follows. And this is why we call it level order traversal. What it will do is it visits level by level the tree. So it starts off at level 0, then it goes level 1, then level 2, then level 3, and level 4. So what it will do is you'll visit all of the nodes in a manner that looks like this. And it will zigzag like this. So just to give you an idea what the level order traversal will look like here. Well, if you just read it off level by level from left to right like this, I'm just going to ignore the leaf nodes, but you're going to find that sometimes this is helpful for us if we want to know what's actually happening with our tree. You're going to see this actually on the assignment. So I have 10, 7, 13. So I'm just reading level by level from left to right. 7, 13. 2, 11, 16, and then 3. So these are all different kind of tree traversals you can do on a binary search tree. I want to stress that the level order traversal you can do just on a general rooted tree as well. But Inorder is special to the fact, especially if we want to ensure that there's an ordering. But you're going to see that we can generalize this idea further. So are there any questions about any of these tree traversals before we proceed? So these are all very neat to run into because they give you ideas for how you can explore a tree. So I thought we would start off with trying some stuff with our binary search tree. So I thought we would first examine what I would consider one of the simplest things we can do with a binary search tree. I thought we would try computing the smallest. So what we're going to do is we're going to talk about smallest, and then I think that'll be a perfect place for us to stop here today. And then we'll talk about the rest of the operations next class. Because I'm looking at the time, I'm like, yeah, we have enough time. We're going to pull this off. So let's talk about smallest. So we're going to try to describe an algorithm for computing the smallest key. Come on, I'm trying to race as fast as I can. What do they put in this whiteboard ink? It's a little tougher today. Okay, let's do this. So, let's talk about the smallest. So, I'm going to draw out a binary search tree. Actually, I'm going to use the same one I have over there. So I got 10, 7, 13, 2, 3, And I'm going to have 11 and 16 just like before. It's the exact same tree I had over there on the left board. So if I were to draw out this binary search tree, what is the smallest key in this binary search tree, everybody? What's the smallest key here? Don't be shy. Tell me what it is. Is it like 16 or something, or is it 11? What is it? It's 2, right? It's 2. 2 is the smallest key. Now, do you remember the binary search tree property? So if I give you a node, I look at it, if it's an internal node, what I can tell you is that if I look at its left subtree, all of the keys in the left subtree, so if I take the node that it's its left child and I consider that subtree, remember, every one of those, if they exist, their key is less than my key. So every one in this left subtree is less than 10. All of the ones in the right subtree are greater than 10. So let's think about this. If all of the ones that are all the keys that are less than 10 are in the left subtree, well, think of it. Okay, so let's look at this tree. Well, the binary search tree property says if I consider the left one, everything is on the left subtree is less than my key. So all these are less than 7. There's nothing in the right subtree except for a leaf node, no key there. So now look at this. I'm at 2 right now. Okay, nothing there. This is bigger than 2. Do you have an idea for how we can compute the smallest? In fact, where is it? Where is it? The smallest key is in the leftmost internal node, right? Exactly. It's in the leftmost internal node. So all you have to do is go far left as possible. That's all you have to do. And that's what our algorithm is going to do here. So let me just write out the pseudocode here, and then we'll come back to its analysis. How does that sound? So I'm just going to give you the algorithm. It's very short. So algorithm smallest, and it takes in the root. So its input is the root R of a binary search tree, and the output is then I'm going to make it so it's returning the node itself, but you can easily modify it so it actually returns the record or its data or anything of the kind. So it's going to be returning the node because we're going to actually use this algorithm probably next day at some point. So the node storing the smallest key, or null if the tree is empty, meaning it has no records in it. If the tree is empty. So the reason why I have to mention this is because in the configuration we have for our binary search tree, when you initialize it, it actually starts off as just a leaf node. So that's actually what the initial configuration of a binary search tree is you just have your instance variable. It's going to be initialized to be pointing at a leaf node. So one of these dummy leaf nodes. That's why I have to mention that. So first, you have the first case. If R is a leaf, so if it's a leaf node, you know you've gone too far, right? But also specifically, you'll have this case right here. So if I give you the root, and it's a leaf node, you know the tree's empty, right? There is no data to examine in this tree at this stage. Otherwise, you're at an internal node. So what we do is we just simply make a pointer that's going to point at whatever R is, kind of like I have a current variable, just like when you traverse a linked list. And all I'm going to do is make it go as far left as possible. So while P is an internal node, so I'm just going to ask if it's an internal node as the condition for my loop. We can do the following. So while it's an internal node, I'm just going to take and reassign P to be the left child. Just like you would if you wanted to get the next node in a linked list. Same idea. Same idea. Left child of P. So I'm just going to reassign P to be the left child of P. Now, just to wrap things up here, because we need to get going. Okay, if I keep going down the left here, if this is still an internal node when I go for enough left, right? When I do this, I take and reassign P to be the left child of P, right? Which brings me down to this leaf node. So if I want to return the node with the smallest key in it, is it the leaf node or is it its parent? Which one? Which one is it? It's parent, exactly. So all I do is I return the parent of P, and that's it. That's the entire algorithm. It's very simple, and all it is just an exploration all the way down the left of the tree. So when we come back next time, we will analyze this algorithm, and we'll see some more operations for our binary search trees. I want to say thank you very much, and have yourself a beautiful day. I'll see you later. Also, have a good weekend, too. I'll see you on Monday, okay?